Hi guys, welcome back to my channel. Today we're going to be talking about the logistic equation. The logistic equation is used when a rate of growth of a population is proportional to the product of the current population and the remaining population. Why is that? Well, we've got two curves here, and one of these curves is an exponential growth curve, and one of these curves is a logistic curve. And if you actually look at the original or the initial first, say, month of a particular population of growth, they actually look very, very similar. And so it can be quite tricky to determine whether or not it's exponential growth or logistic growth. But why does this start to eventually slow down and start to taper off and reach this equilibrium point? Well, simply put, it's because of this carrying capacity. Because in the real world, growth is often limited by factors such as sunlight, water, space, or food. So a population reaches that carrying capacity when resources have been not exhausted, but when resources are being used in equilibrium. So the rate of reproduction is equal to the rate of death of that particular population. So really great example, if you were talking about the rate of growth of a virus in a particular population, initially what you might see is you might see that quite a few people are getting sick very, very quickly. However, eventually, it's infected everybody in the community, and so the rate of growth starts to slow down and starts to taper off a little bit. All right, let's go through and let's do an example now with some maths. So a rumor is spread at a local high school by a group of 5 teenagers. After 1 week, 40 students have heard the rumor. If the school has 800 students, determine how long it will take for half of the school's population to find out. Well, we know that this is a problem that has some sort of carrying capacity because the school has a maximum of 800 students, so no new students are going to hear it after that point. So the rate of growth of this population of student who's heard the rumor is proportional to the number of students who've already heard the rumor multiplied by the remaining number of students. So this here is going to be our carrying capacity. And this value for n is going to be our value for our population at any time t. So what we can do is we can rewrite this as dn dt is equal to k n p minus n. Now, we have some information here that we can substitute in, and we know that in our particular situation, p is equal to 800. Since we have n on this side of our equation, I'm going to want to integrate or differentiate with respect to n, so I'm going to flip this derivative. And now I can go ahead and I can integrate both sides of this function with respect to n. Now that we've integrated this function, and I've just done this using partial fractions, and I've done this off screen. If you are interested, I do have other videos that are on partial fractions. So we're going to go ahead now and substitute in some values that we know so that we can solve for c. So we know that initially there is a group of 5 teenagers that's spreading that rumor. So when t is equal to 0, n is going to be equal to 5. So I've substituted in my values and I found an exact value for c. Now you can go ahead and you can substitute the decimal in here, but since I'm working in logs in my formula, I actually think it's a little bit easier to work in logs for my value for c as well. And then what I can do is I can actually simplify this because when I pop this in my equation, 800 kt is going to be equal to ln n over 800 take n, plus ln of 159. And when we add logs together, we can multiply these inside values so that we have 800 kt is going to be equal to ln of 159 n over 800 take n. And so that's including our plus c term now. All right, so let's go back and let's actually answer the original question now. So after 1 week, 40 students have heard the rumor. So now that we know that after 1 week, 40 students have heard the rumor, we can go ahead and solve for our value for k. So substituting into our formula now, we get 800 multiplied by 7k is going to be equal to ln of 159 times by 40 all over 800 minus 40, which is going to be 760. So we can go ahead and we can divide through both sides. This is going to be 800 times 7 is going to be 5,600. So if I divide both sides by 5,600, I'm going to get my value for k. And now that we've got our value for k, what we can go ahead and do, we can substitute that into our expression and then determine when half of the school finds out. So we know that n is going to be equal to 400 when half of the school finds out, and we're trying to solve for t. So after substituting in my value for k that I've determined and substituting in my value for n, because half of the school would be 400 students, I've determined that after about 16.7 days, the rumour is going to have spread to about half of the school. So what we can go ahead and do now is we can go ahead and verify this solution graphically, because we do have an equation here. So let's rewrite this in terms of t. So t is going to be equal to ln of 159n over 800 minus n, all over 0.303. So we can go ahead and we can graph this particular function now, if I can draw a nice straight box. So I've just graphed this using Desmos. Now remember, because we've integrated with respect to n instead of with respect to t, then we're actually expressing this in terms of the independent variable. So that's why I've put x is equal to this particular function. And we can see here that when my population is equal to 400, that's going to be after about 16.7 days, just as we predicted from our calculations. All right, so let's summarize what we've done here. So we've determined that when there is some sort of carrying capacity, that the rate of change of a population is going to be proportional to the product of the number of people who are affected. So it could be a virus, or could be number of people who've heard the rumor or something like that, multiplied by the remaining population. So the remaining number of people who've not yet heard the rumor or contracted the virus or whatever it is. So what we can do then is we can express this using KNP take n. Then what we did was we went ahead and we rearranged and integrated with respect to n. Then lastly, when I had this function, I would have expressed this as some function of n rather than expressing this as a function of t. And then we went ahead and substituted in those values to solve for our particular problem that we were graphing at the time. All right, so that is how logistic growth works. In the next video, what I actually want to talk about is I want to talk about how we can determine whether or not it's exponential growth versus logarithmic growth, because as you saw initially, both of them sort of start off as like this very curvy sort of function, but the difference is that the exponential function continues to grow, whereas the logistic function starts to slow. So using that, we can start thinking maybe about our rates of change and seeing if we can determine whether or not it's exponential or logistic growth from there. All right, guys, hope you enjoyed. I'll see you in the next one.